Alright, well, we had hoped to have 4 videos, but I think we're going to have 5. One, we kind of gave the instructions for how to draw those structures. The second one we just looked at had 3 practice problems, and this one we're going to finish 2 more. Then we'll get to shaping the structures and getting into polarity. So kind of, again, remember, we have to be able to build them, we have to be able to shape them, and we have to set sort of what it looks like in terms of polarity. And we're going to, I guess, be on 5 videos in order to do that. The last problem we tried was SO3. I just want to mention some things about SO3. And formal charge is maybe something that's going to have to come up here. What are the formal rules for determining formal charge? Formal charge is determined by taking the element and the number of valence electrons that it has in the periodic table. So kind of number of valence electrons as an atom. So for sulfur, that's going to be 6. And what we do is we subtract 2 kind of types of electrons from it. The number of lone pair electrons, I'm going to just say lone pair electrons, I mean, like if you had a pair of shoes, it's still 2 shoes. We subtract from that given starting number that that atom brings from the periodic table. We subtract number of lone pair electrons minus, now we take, instead of in a bond, you don't take both of them. So we can just say number of bonds that are in that structure for sulfur trioxide. So we can kind of use this general rule, this mathematical expression. The formal charge is the number of valence electrons for the atom, not given the structure that it's in. Sulfur trioxide, I don't care what the structure is. I'm just talking about sulfur. Sulfur has 6 valence electrons. And now to know this part, I need to see what kind of structure is drawn. This part is only determined by the atom, sulfur. We're determining the formal charge for sulfur. So let me just give you one resonance form that we had. We had this. We had a negative here and a negative here, and it had, for oxygen, there's 6 valence electrons. Sorry, those dots are a little bit off. And I had said by Daniel Gonzalez rule, we can kind of set the O's, and I'm going to stay with that. This was a negative because it had only 1 bond. This was a negative because it only has 1 bond. And I said this one was +2 only because, and I should have stayed with this, these are 2 negatives and we got to have it balanced because this is neutral overall. So we said +2. But I'd like to formalize how I know that for sure. Well, let's look at this structure. We know that sulfur, as far as an atom from the periodic table, has 6 valence electrons. So I'm going to subtract from that 6 the number of lone pair electrons for sulfur. Well, that's 0. He's got no dots off of him. And now I'm going to take each bond. 1, 2, 3, 4. Double bond. There's still 2 bonds in there. So again, taking these together, if we add that up, I guess it's going to be minus the number of lone pairs, which is 0, minus the number of bonds, which is negative times positive is negative. So that would be equal to 2. Its charge would be +2. Now, I also said that you can have different resonance forms outside of what we drew for sulfur trioxide. And one I'm going to go ahead and show, which they seem to think is more common, would be this one where we have all the negatives. I'm not going to draw in the dots for the oxygens. We're going to just leave it with this bond given back to the oxygen up top. So all of them are negative. Each of these oxygens would have 6 dots around them. For this structure, we'd still say 6 minus, now it has no lone pairs, so we'll just say -0, minus the number of bonds is 3, so that would be now a +3. The sulfur here would have a +3 charge. Then one last one, and this is one that blows students' minds, is we can have around sulfur, you can have more than 8 electrons. It's because it's a 3rd row element and it has some d orbitals it can make use of. So 1, 2, 3, 4, 5, 6 bonds, that's 12 electrons. This is a valid resonance form or Lewis structure for sulfur trioxide. We're not going to draw this, I guess. I guess in the notes I didn't consider this one or this one, but they're both valid. This one would have a different formal charge. Now 6, still taking off with just sulfur, having 6 electrons. Again, we're just kind of keeping this all for sulfur is the atom we're looking at. Minus, now it has no lone pairs. Now it has those 6 bonds. 1, 2, 3, 4, 5, 6. So in this case, the sulfur here would have a 0 formal charge. Alright, I'll stop there. Let's do those last 2 problems. And this, again, is just helping you to know the formal rules for formal charges. I guess that kind of came up. Alright, let's finish in the next 2 practice problems and be done. Alright, so we know we have to find number of valence electrons always for any given molecular formula. But hey, they have a negative charge here. What do I do with that? Well, if it's a negative, that means you have one more electron than a proton within this structure because it has an overall negative. So what I just do is if it's a -1, then I add one more valence electron to my count given the charge. If it had been a +1, then I'd take one away. And same sort of issue with -2 or +2. So let's still consider the nitrogen. Nitrogen is 5 spots over. So we'd say 5 plus, there's 6 valence electrons for oxygen, but we have 3 of them. But now with that negative charge, we're going to add 1. Because we're talking about valence electrons. So that together is going to give me 24 valence electrons that have to go in to this structure we're going to draw for NO3 or nitrate anion. The middle, who has the greatest need? Well, that's nitrogen. He needs 3 bonds. The oxygen we know only needs 2. So the middle would be nitrogen. And then framing around it, I know I have to have everybody connect back to nitrogen. And I'm going to add in the lone pairs, but I know I already have 2, 4, 6 electrons, so I need to add 18. So I think you guys know how that's going to go. 2, 4, 6, 8, 10, 12, and 14, 16, 18. If you count all those electrons up, the 6 given these lines, 2, 4, 6, plus all the dots, you'll get to 24 electrons. So this is our frame now with all the electrons added, valence electrons from the outside on the O's. And now we're going to have to probably drop because N is not sulfur. It can't go above 8 electrons, but it needs to get to at least 8. Everyone in the 3rd or 2nd row at least needs to get to 8 in most cases to be most stable. Again, 3rd rows can violate and go above 8. So let's drop 3 different ways. I can drop from this O, or I can drop from this O, or I can drop from this O. So it's kind of like the one we just saw for sulfur trioxide. So I'm going to again draw those dots. These did not change. And let's hit formal charge as we go here. When we know the NO rule is going to work, the kind of the Daniel-Gonzalez rule. If the atom has, and this is for N's and O's, if it has less than what it wants, it's going to be negative. It has only 1 bond, so it's going to be negative. Same thing for this one. And N here has 1, 2, 3, 4 bonds off of it, so it's going to be a plus. Well, that works out because a negative, 2 of them with 1 positive, does give us an overall -1 charge. So now we're just going to continue this and do it with other oxygens. Oops, there's just 2 there. Should have centered it. So it's going to be a negative here, and a positive still here. And then the last one, of course, we're going to be on this oxygen. And the positive is here. Negative and negative. And again, it's a mixture of all 3. And these are the only 3 resonance forms for nitrate. But we know again then that the negative charge is kind of equally spread around those 3 oxygens, and the positive charge, there is a formal positive charge on the nitrogen. Looking good. That was a hard one. We're going to end with an easier one where we don't have resonance. This is phosphorus pentachloride. So again, phosphorus and sulfur are third row elements, so they can have more than 8 electrons. And if you're don't know which one to pick as a central element, and it's sort of tied when it comes to who has the greatest need for bonding, always pick the third row element. Now here, phosphorus needs 3 bonds at least to get to the right side. It's going to have more, because we have 5 chlorines, but we're going to put him in the middle. We're going to frame around it. So I'm going to put 5 around it. Oh, isn't there something I forgot to do? Dr. P. What did you forget to do? Oh, valence electrons. We need to make sure we always know what number we're heading to. Phosphorus is like nitrogen. It has 5 valence electrons. Our chlorines each have 7, so we have 5 times 7, which is 35, plus our 5 is 40 valence electrons. That's a lot. So I have a lot of dots I'm going to add in, and I'm just going to ask that you trust me on this one, or let's just count as we go. Here we go. I'll have the let's put all the lines in. And given those lines, we are now down 10, because 2, 4, 6, 8, 10. So all I need is 30. I need to add in 30 dots. Here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, yay, we're done. That's what the Lewis structure of phosphorus pentachloride is. Boom, we're done. Thanks.